So now let's consider an active bandpass filter. So what we're going to look at is we want to create an active bandpass filter, which is going to provide the frequency response shown in this plot here, but we want to create this filter using the active filters that we've already discussed in the previous two videos. So take a minute and see if you can think about how to combine those previous filters in order to make a bandpass filter. So go ahead, pause the video, think about that for yourself for a while. And so we notice here we have sort of our typical our bandpass response. We have some center frequency omega naught. We have our omega 1 and omega 2 frequencies, our corner frequencies, which are 3 dB below our maximum point. So we have some gain K that is occurring at our resonant frequency here. And then we have 0.707, which remember is just 1 over root 2 times K, and that's occurring at our two corner frequencies, omega 1 and omega 2. So how can we provide this? Well, we can sort of think of combining a low pass and a high pass filter in series such that our high pass filter is blocking things below a certain level, our low pass is blocking things above a certain level, and if we sort of, basically if we think about it this way, let's sort of draw this. We have our high pass looks something like this. So we have some omega high, and then our low pass is going to look something like this, where we have this is our omega low. And so what you can see is by adjusting this omega high and omega low, we can get them such that we have some area in between the two that our signal is being passed and outside it is being blocked. So let's take a look at that circuit and see if we can analyze it in a little more detail. So here I have a circuit that will let us achieve an active bandpass filter, and so we see it essentially has 3 stages. So over here on the far left, we have a low pass filter where we have our capacitor in our feedback network. So this is going to be a low pass. And so this low pass filter is going to set our omega 2. So if we come back up here to our plot, we see our omega 2 is this over here. So we're saying we want to pass everything below omega 2. So this would be our omega 2 in this case. So the next portion here is our high pass filter. So in the middle here we have our high pass. And so this high pass filter, which has our capacitance and the input impedance, is going to set our frequency omega 1. So we come back up here and we can see this is our omega 1. So it's saying pass everything above omega 1. So here is our omega 1. So then of course to get this gain K, we also have to include a gain stage, which we see is here at the end. So this right here is our gain stage. And this is just an inverting amplifier. So inverting amplifier configuration, which is providing us gain. So as we recall from our op-amp unit, if we have cascaded op-amps, our transfer function is just going to be the product. Well, when we talked about op-amps, we were talking about gain. We said the gain is the product of the individual gains of the stages. And so the same thing is going to be true here. So our overall transfer function is just going to be the product of those transfer functions of the cascaded systems. So our transfer function is the product of the individual transfer functions. So same idea as we saw with our gains for cascaded op-amps. So we can come here and we can write our overall transfer function h of j omega. Remember, in general, that's going to be output over input. In this case, we're talking about voltages. So for our low pass filter, we had that it was -1 over 1 plus j omega C1 R1. For our high pass, we have that it was negative j omega c2 r divided by 1 plus j omega c2 r. And then for our gain stage, it's just our inverting amplifier. So we have it's negative RF divided by RI. So we get something that looks like this. And so again, we have that we can determine specific values sort of from inspection of these equations here, or by comparing our circuits above to our previous analysis for our low pass and high pass active filters here. And so what we can see is that our upper 3 dB frequency, which we said was set by our low pass filter, so upper 3 dB frequency is equal to omega 2 equals 1 over RC1, and so that was from our low pass. Our lower 3 dB frequency we can see is equal to omega 1 equals 1 over RC2, and so that was from our high pass. And so something I meant to mention earlier, but notice in this case we've just have R values for most of these resistors, and that's just for simplicity. Of course, if we wanted to, we could come in here and change that, but for this first run at our analysis, it's easier to just keep those as one fixed value. And then of course we can change the frequency because we have control over these capacitors, so these are still unique. Okay, so we can define our two 3 dB frequencies, omega 2 and omega 1, in terms of our resistances and capacitors. And then beyond that, we said that really these bandpass filters have the same equations as our series resonance. So same equations apply from series resonance. So in our series resonance, and so I'm just going to write down some of the key ones, we know that our resonant frequency, or our center frequency, is the square root of omega 1 times omega 2. We know that our bandwidth is omega 2 minus omega 1. And we know that our quality factor is equal to omega naught divided by B. Okay, so we found how to create this band pass filter, but one thing is still left unknown, and that is what is this gain value K during our pass band here. And so it's not as straightforward as we saw for our low pass and our high pass filters, where we could just sort of look at one extreme and we had the gain of the inverting amplifier. But here what we need to consider is sort of we have effects coming from both of these high and low pass active filters. So let's take a closer look at this equation here. And what we're going to do is we're going to take the expression for our omega 2 and our omega 1, and we're going to put them in for these terms. So for instance, our omega 2 we're going to use to substitute for the C1R1, and our omega 1 we're going to substitute for this C2R2 here. So let me come down here and rewrite that. So what we're trying to find is we want the gain during our pass band. So our pass band gain K. Okay, so first let me start by rewriting. We have h of j omega is equal to negative RF divided by RI. And now rewriting this in terms of our 3 dB frequencies, we have 1 divided by 1 plus j times omega divided by omega 2 for our low pass filter. And for our high pass filter, we have in the numerator j times omega over omega 1, and in the denominator 1 plus j times omega divided by omega 1. Okay, so let's clean this up a little bit. That's a little messy, so we'd like to get rid of the omegas in the denominator. So let me move this over a little bit for clarity, because what we're going to do is we can multiply this term for our low pass filter by omega 2 divided by omega 2. And for our high pass filter, we can multiply that by omega 1 divided by omega 1. And so if we make that adjustment, what we see is we have h of j omega is equal to negative RF over RI. And now this is going to become omega 2 divided by omega 2 plus j omega. And here we have j omega divided by omega 1 plus j omega. So a lot easier to look at now. And of course we can just sort of combine those two terms for our high pass and low pass filters. So we have negative RF divided by RI, our gain stage, just sort of hanging out front there still. And now combining those two terms, we have j omega times omega 2, and in the denominator, we're going to have omega 2 plus j omega times the quantity omega 1 plus j omega. And so what we're going to do now is we want to sort of factor out that denominator. So we can say this is going to be equal to negative RF over RI times, so in the numerator we're just going to have that j omega omega 2, and in the denominator, if we factor that out, what we get is omega 2 omega 1 minus omega naught squared. So I don't want that yet, so plus j omega times the quantity omega 1 plus omega 2, and we get something that looks like this. And so remember, this is our transfer function, h of j omega. Okay, so what we're interested in though, if we go back to our plot, of course whenever we're plotting sort of this frequency response, we're plotting the magnitude of this transfer function. So let's describe the magnitude then from this equation. And another thing I'm going to do is I'm going to go ahead and use for our frequency, a frequency omega naught. And the reason is because that's the frequency we're interested in. We're looking at our gain at this frequency. So in this case, what we have, and so it looks like I have dropped a negative sign somewhere. So we should have this negative sign right here canceling out, and let's see where that's coming from. So looks like that's canceling out from somewhere in the numerator. So I'm going to go ahead and get rid of that for now. And so basically, if we are then looking to find the magnitude of this, we just have this RF over RI, and we're multiplying that by this numerator. We have omega times omega 2, but remember we're looking at omega naught, so I'm putting in omega naught. And then we're going to have the square root of the quantity of omega 2, omega 1, minus omega naught squared. So all of that is squared, plus this omega times the quantity omega 1 plus omega 2, and then all of that squared as well. Okay, so it might at first glance look like we've just made everything a little more difficult, but in reality we can simplify this a lot if we just keep in mind our basic definition for our resonant frequency omega naught. We said that's the square root of omega 1 times omega 2. And so if we substitute this definition in here, so we can see that this right here is actually equal to omega naught squared. So then we're going to have omega naught squared minus omega naught squared, so this term here is essentially going away, and we're just left with the term on the right. So what we have then is the magnitude of h at j omega naught is equal to RF over RI times, in our numerator, omega naught times omega 2, and then the denominator term, it's the square root of the squared, so it just comes out omega naught times omega 1 plus omega 2. And of course now we can see this omega naught is going to be canceling out. And now we have our passband gain, because this is where we plugged in our omega naught. We know at omega naught from a plot, our gain should be k. So therefore we can say our passband gain k is equal to RF divided by RI times omega 2 divided by omega 1 plus omega 2. And again, keep in mind this is for this particular circuit. This isn't necessarily a general equation for all passband circuits. This is for this particular circuit. And another thing that we can note is, of course, we have control over this passband gain K through our RF and R1 at our inverting stage, but we also have some influence in our passband gain based on where these 3 dB frequencies are. So as we're adjusting our capacitor values or that generic resistor R value, we're changing our omega 1 and omega 2, which is in turn influencing our passband value, our passband gain value K.